Hello guys, so I'm quite excited to start this linear algebra series. In this video and in the upcoming series of video, we are going to understand various topics in linear algebra, which will be super important if you are planning to become a data scientist or a data analyst. We will be seeing some of the important concepts and where it will be specifically used if you are learning machine learning, let's say deep learning, and what are the core concepts that we really need to know if you really want to become a data scientist. So in this video, I will be talking about what exactly is linear algebra. We'll go through the definition, and after that, we will be seeing some of the main applications of linear algebra and how we can probably use linear algebra in various techniques specifically to solve use cases with respect to machine learning, deep learning, and data science. So all these things will be covered in this specific video. So first of all, let us go ahead and talk about the definition of linear algebra. So linear algebra is a branch of mathematics that focuses on the study of vectors, vector spaces, also called as linear spaces. Then you have some topics like linear transformation. Then you have system of linear equations. It provides a framework for understanding the properties and operation of mathematical objects. Okay, this is really important to understand, which can be represented using matrices and vectors. So specifically in linear algebra, if I talk about, trust me, this is the foundational concepts that you really need to understand if you are studying machine learning, deep learning, right? Even concepts like natural language processing, where your input data is in the form of text, and even in computer vision, if I probably talk about images, right, where you are specifically working with images or video frames, everywhere some or the other concepts of linear algebra will be specifically used. In linear algebra, if I talk about some of the core concepts that we will be seeing are like what are scalars, okay, then we will be getting to know about concepts like vectors. Then we will be discussing about matrices, okay, matrices, along with that mathematical operations on matrices, mathematical operations on matrices, mathematical operation of matrices. Along with this, we'll also be seeing some techniques which are called as linear transformation. And this specific technique of linear transformation will be used in one of the machine learning algorithm, which is called as principal component analysis. What exactly it is, we'll discuss about it. Other than this, some of the concepts like eigenvalue, eigenvectors, we will try to learn about this also, right? And still there are more topics. It is better that I list them down as we go ahead and complete the series, okay? So here you can actually see these are some of the core concepts for everyone. Probably you should have some amount of information about it. And our main aim in this series of video is to understand linear algebra, how it can be specifically used in the data analytics industry, specifically to solve data science use cases. Okay. Now again, linear algebra has huge number of advantages, right? A huge number of applications. Sorry, it will be obviously used in various concepts in physics. If I talk about mathematics, there also it will be used. But our main aim is to learn this as a computer science grad, right? So computer science student, let's say if you are a computer science student, how this will be specifically used, and our core area of subject will be data science, okay? Data science. Even if you know about graph knowledge, right? And recent techniques of graph knowledge are also using some of the linear algebra. So internally they use something called as vectors and vector space in order to create your entities and all, right? One of the core concept of text embedding, where we use NLP, there also we'll be specifically using vectors. Okay, so we'll discuss more about this as we go ahead, right? Now let us go ahead and understand. I've written normalization and standardization. I will discuss about this later, but let me just go ahead and talk about some of the important applications, some of the important applications in some applications of linear algebra. Okay, and again, this will be discussed in terms of as said, as a computer science student, I will not be talking about use cases with respect to physics or mathematics. Mostly the use cases will be based on the kind of work that we specifically do in data science. Okay. Now, first applications that I really want to go ahead and write. I will go ahead and write about data representation and manipulation. Now, in order to understand about this important application, that is data representation and manipulation, let me take one specific example and what kind of use cases that we solve with this example. So let's consider that I have a data set. Okay. So whenever we have a specific data set, specifically, let's say that one of the tasks in data science is that I need to create a model which will be able to predict something. Okay. Which will be able to predict something. So let's consider this as an example. Okay. Let's say the data set that I'm actually going to take is something called as house price data set. Now in this house price data set, let's say I have some of the features like area of the house, let's say number of rooms. Third feature can be something called as location. Okay. And finally, my output feature will be something like price. Now here in this use cases, I am planning to probably design a model. This model work will be that it will be taking area as the input, number of rooms as the input, and location as the input, and it should predict the output, that is price. So usually in this problem statement, what happens is that whenever you are trying to solve this problem statement over here, let me go ahead and talk about something very important over here. These features that you see, area, number of rooms, and location, these are called as independent features. Okay. These are called as independent features. So here I will just go ahead and write it as independent or input features. And this is basically my output feature. Okay. Now I will be having different values over here. Okay. I will be having different values over here. Okay. And let's say this is my entire data set. Let's say it has somewhere around 10,000 records. You know, some of the values will be like, let's say the size of the house is 1200 square feet. Let's say there are 2 rooms and the location is Bangalore. And because of this, let's say the price is somewhere around 45 lakhs INR. Okay. So if I consider this as my input data, so here it says that these are my input features, and based on this, we need to predict what is the price of the house. Now understand, as a human being, because our brain are so well trained, you know, we know, okay, fine, if the area of the house is more, if the number of rooms are more, and the location is somewhat in a tier 1 city, obviously the price is going to go high. But if we are training a model, you know, completely from scratch, model does not understand any of these features, right? It does not understand about area or number of rooms or location. All it understands is this numbers and how the relation of all this input feature is with respect to the price. It needs to really understand about that. Now, if I probably consider this data, right? So this data over here, how it is represented to the model, this is represented in the form of vectors. So here I have, what exactly is vector, I will be discussing in the next video in much more depth, right? But if I just give you a basic definition of vector, it is nothing but it is a list of, or you can just define it as, it is a list of numbers over here, right? So over here, I have some list of numbers, area, number of rooms, location. This location will also be getting converted into vectors or some number, right? And based on this list of vectors, I have the price that is included in this particular vector. Now, based on this list of vectors, you will be able to see that my model will be able to even quantify the relationship. Quantify the relationship between area and price, because price is my output feature. It can quantify the relationship between area and number of rooms. It can even quantify the relationship between every other features, right? And whenever we say quantifying the relationship, I'm just considering that, let's say if I have X and Y feature, I will be able to understand if X is increasing, whether Y is increasing or not. If X is decreasing, whether Y is decreasing or not. So this relationship, or if X is increasing, whether Y is decreasing, or if X is decreasing, whether Y is increasing, right? So this relationship, it will be able to quantify. Now, when we say that it will be able to quantify, that basically means we will be thinking about concepts such as covariance and correlation. So this concept will also be covered as we go ahead, because these concepts are something important, and this will be covered in stats. Okay, it will be specifically covered in statistics. Okay, but initially we'll get an idea with respect to this linear algebra. So here you can see data representation and manipulation. So when we are training all these specific models, we basically represent this entire data in the form of vectors, and what internal operation is basically happening, there a lot of mathematical equations will get calculated. And in this scenario, we basically say this as a regression problem statement, right? I will also probably upload a video with understanding the mathematical intuitions behind that as we go ahead. Okay. So this is basically about the data representation. So here, linear algebra provides the tool for representing and manipulating data in the form of vectors, because see, internally some or the other calculation will happen, right? How much factor this area, let's say if this area is increasing, by how much factor this price may increase, right? So that factor, if we really need to understand, it will be able to, we'll be able to calculate after doing multiple matrix calculations and all, and which will show that how these things will basically work. Okay. Now, two important terms that I've used over here: data representation and manipulation. Here, first of all, linear algebra provides a tool for representing and manipulating this particular data in the form of vectors. Okay. And if I see, whenever we talk about vectors, right, vectors can be single dimension. And if I just take an example, let's say this is the notation of a vector. Okay. Let's say in this vector, I have one element, let's say 1200, which is my area, right? So this basically becomes my one dimension vector. Okay. Similarly, if I represent another vector where I take just two features, okay, let's say I take 1202. So here I have two dimensions, right? So this is basically two dimensions. Similarly, if I take this location, it will become 3 dimension. If I take price, it becomes 4 dimension, right? So vectors can also be represented in the form of dimensions. Even in deep learning techniques, if I talk about like image processing, there also we'll be seeing that whether we'll be working in 1 dimension, 2 dimension, or 3 dimension. Okay. Now, linear algebra, one more important thing is that right now, see, as a human being, whenever I say 2 dimension, what does this basically mean? We design a coordinate system. Let's say this is my output feature called as price, and this is my area. Okay. If I try to plot this in a 2 dimension, you'll be able to see that as the area keeps on increasing, the price will also keep on increasing, right? So this plotting of every points, let's say this particular plot, this particular point is the vector of 1200, 45 lakhs, right? So this basically becomes a 2 dimension vector, right? So when I say 2 dimension, that basically means I'm plotting a point, and in this point, I will be having an X coordinate or Y coordinate. This is my X coordinate and this is my Y coordinate. Let's say that this X and Y coordinate are nothing but 1200, 45 lakhs, right? Similarly, the different point will be denoted by different coordinates. So in this case, since I'm using 2 different values, so this basically becomes a 2 dimension vector, 2 dimension vector. Now you may be thinking, can we probably draw a 3 dimension vector? Yes. Let's say if this is my area, this is my price, this is my number of rooms, let's say. So here I will go ahead and write area, price, number of rooms. Now let's say there are points. There are points like this, this, right? And these all points are basically decided on these 3 values. Okay. That basically means every coordinate is represented by a vector of X, Y, Z. X can be area, Y can be number of rooms, Z can be price. right? So this basically becomes a 3-dimension, right? Now you may be thinking, Krish, can we also draw 4-dimension? See guys, we are human beings, max to max, we can actually see 3-dimension. We cannot see 4 dimensions, right? It is, if you can see 4 dimensions, that basically means you are having a supernatural power. Okay. So max to max, we can only see 3 dimensions. Okay. Now, the best thing about linear algebra is that one of the important points, why specifically it is used in machine learning, it is that it will be, linear algebra works really well with higher dimension data. Okay. Now, see over here. If I consider this 1, 2, 3, 4, there are 4 features. Obviously, 4 features, I cannot see 4 dimensions, right? When I say linear algebra works with higher dimension data, that basically means even though these features are in 4 dimension or 5 dimension or 5,000 dimensions, the kind of matrix calculation, the type of vector calculation that can be specifically done with respect to high dimension data, it will give us fabulous result with linear algebra. How that things will happen, I will talk about it in the future. But let's take one example. Let's say if I have somewhere around 5,000 dimensions in my data, or let's say that 5,000 is too much. Let's say that if I have 500 dimension, 500 dimension basically means 500 features. In linear algebra, there are concepts, right? The concepts which we specifically use in dimensionality reduction. Okay. These features, when we apply dimensionality reduction, it will try to convert into, we can even convert this into 2 dimensions. This is the power of linear algebra. How this thing can be happened, we will learn about a concept which is called as PCA. Okay. So that we human being can also understand, when it converts into 2 dimension, what is the pattern the data actually follows, right? And just by seeing this data, right, we can also even find out the relation, whether X is increasing, Y is increasing, or X is decreasing, Y is decreasing, or whether X is increasing, Y is decreasing, or whether X is decreasing, Y is increasing, right? We can even find out this particular relationship. Okay. This is the most amazing thing about linear algebra. It works really well with higher dimension of data. We'll be able to understand about the data a lot. Okay. So this was the first point, that is that we'll be able to represent the data well. We'll be able to perform different manipulation and all, because at the end of the day, every values over here will be converted into vectors. When we say vectors, dimensions, they are one and the same. Okay. Now, the second thing where it has some amazing application is nothing but it is in our machine learning and artificial intelligence. Second point. So here I will just go ahead and write my second point. The second important applications where it can be used is called as machine learning and artificial intelligence. Okay. Now, when I say machine learning and artificial intelligence, one of the core concept that we do in machine learning is basically train our model. So train our model basically means what? Okay. Let's say I have this feature, which is called as price, and I have, or let's say if I have the input feature called as size of the house, I should be able to predict the price of the house. Okay. Usually in this scenario, when I have my entire training data points, so this is my data points that will be there, right? So in model training, what we do is that since this is a regression problem statement, one of the basic algorithm that we may apply is something called as linear regression. Linear regression will be creating this best fit line, Now with this best fit line, what happens is that with respect to any data points of size, we will be able to predict the price. Right? Now this process of creating a model wherein we give any input and it should be able to predict the output, that is basically called as model training. Okay. So in model training, specifically, we rely on linear algebra. Why? We rely on linear algebra. Why? Because in order to train this model, we will be doing multiple matrix multiplication, or not only multiplication, I will probably say matrix operations, matrix arithmetic operation, matrix arithmetic operation. So we will be specifically doing this, okay? And here we are also going to use something called as linear equations. One of the most common linear equation, if you remember, equation of a straight line. Equation of a straight line. So equation of a straight line can be given by something like ax plus by plus c is equal to 0. And many people, many books also, if we refer, it will be given in this equation, y is equal to mx plus c. Now, what does this basically mean? We will probably go ahead and understand about one of the regression algorithm later on, so that you'll get an idea with respect to this. So here, these are nothing but these are called as linear equations. Okay, linear equations. So extensively linear algebra concepts will be used over here. Okay. So one of the most important application in machine learning and artificial intelligence is about model training. Coming to the second important point over here, where exactly it is used. It is called as dimensionality reduction. I've already told you what exactly is dimensionality reduction. So here, obviously, as you know, as a human being, we cannot check or we cannot even visualize data of higher dimension. So what happens is that inside this dimensionality reduction technique, we use an algorithm which is called as PCA. Now PCA uses this linear algebra concept. What concepts we'll be specifically using over here, which we'll discuss in the future, which is called as eigenvalue and eigenvector. And with the help of this eigenvalue and eigenvector, we will be able to reduce from higher dimension to lower dimension. Higher dimension to lower dimension. Now, how this will happen, again, we will discuss about this as we go ahead in the series of videos. Okay. Coming to the third one. Okay. Specifically in neural networks. So in deep learning, there is a concept of something called as neural networks. So in neural networks, there is a concept of something called as forward propagation. Forward propagation and backward propagation. Backward propagation. So just to give you an example, again, as I said, neural network need not be these topics may not be a prerequisite, but if you just have some amount of idea, this will be really helpful for you all to understand. See, and let's say one of the example is this. I have a neural network which has two input layer. So basically two input nodes. Okay. Let's say that I have one hidden layer which has 3 hidden neurons, and finally I have an output layer. Okay. And this, if you don't know, just consider this like this, right? It will be interconnected, right? This all will be interconnected. And finally we get the output over here. Okay. So here, let's say if I have an input feature like area and I have something called as price. Let's consider in this way. Okay. Let's say I have area and number of rooms. These are my input feature. And then we have the output. Okay. So this we will consider as our F1 and F2 feature, and this will be my output feature. So usually in neural network, what we do, we give this F1 and F2 feature over here. Okay. Then when this feature is basically sent, we initialize some weights over here. W1, W2, W3, W4, W5, W6, right? When we say W1, W2, W3, W4, W5, W6 weights, here you will be able to see that these are two inputs, right? And we are connecting it to the 3 hidden neurons in the hidden layer. So this basically becomes a 2x3 matrix. 2x3 matrix of what? Of your input and the weights, right? Because weights is also over here, right? So here I have 6 weights that are probably coming up, right? So what happens? This is my input. Let's say my input is F1 and F2. And my weight, since I have 3 hidden neurons, it will be nothing but W1, W2, W3. Sorry, it should be W1, W2, W1, W2, W3. Yeah. Then similarly, you will be having W4, W5, W6. Now, in this scenario, when you probably see from one input, you're going and multiplying with the next operation that you specifically have over here is something called as matrix multiplication. You have to multiply these inputs with these weights. So here also extensive matrix multiplication will be required. Matrix multiplication is required. And this is just the first step. I do not want to teach you more forward because I'm not considering this as a prerequisite. One of the operation will be that we need to take all the inputs and multiply with all the weights, right? Then we have to take the another inputs, then multiply with all the weights, right? So here, if you see over here, this involves matrix multiplication. And when we do this for this matrix multiplication as we go ahead forward, this is called as forward propagation. And in backward propagation, we update this weights. So for updating this weights also, we use something called as chain rule of derivative. That will probably come up in differential calculus. Okay. So differential calculus is also required in this concept. But if we are doing this forward propagation, here you will be able to see that we have to probably perform this matrix multiplication, right? So this matrix multiplication, how do you perform? If you have the idea about it, then you will be able to do it. Not only matrix multiplication, we also go ahead and add a bias in every neuron. So we also have to do the addition operation in matrix multiplication. So it is important that at the end of the day, linear algebra is the core concepts even in machine learning, neural network, even in deep learning and all. Okay. Now coming to the third and the most important application, even in computer graphics. So if I probably consider this computer graphics. Okay. And don't worry guys, I will explain each and everything, like what are the core concepts that will specifically required in linear algebra. We'll discuss about it. We'll talk about scalar, vectors, matrices, mathematical operation, what is linear transformation, how do we basically go ahead with eigenvalue and eigenvector. And even in deep learning, if you don't know, even in neural network, right? How do we train a neural network with the help of GPUs? So in GPUs also, you have something like cores, okay? Now, the reason GPU trains very much faster because all this matrix multiplication will happen parallelly. Right? So if you have an idea of neural network, we use something called as TensorFlow as a package. You know, there's a library called as TensorFlow, which will actually help us to create this neural network. So here, every values of this matrix will be converted into tensors. And these tensors are probably trained in this GPU completely parallelly, right? All the operation will happen parallelly. And that is how the neural network is trained fast. Right now you have generative AI, you have so many LLM models that are probably coming up, right? These are extensively used in, these are trained in very huge GPUs, you know, H100, A100, that kind of GPUs, you know, where a lot of electricity will be required. So in short, this GPU has a lot of cores, you know, the cores will actually support a lot of parallel operation. Now, if I talk about this computer graphics, okay, let's say that I have an image, okay. So image also, if you have some basic idea, let's say that I want to represent this image in the form of pixels. Let's say this is 4 x 4 pixels. 1, 2, 3, 4. Now every value over here in this pixel is between 0 to 255. Specifically, if I talk about RGB image, you will be having this 3-dimension images like this, right? One more and one more. This will be R channel, G channel and blue channel, right? So every pixels will be specifically there. Let's say if I want to perform some of the important operation on this particular images, right? What kind of operation? Let's say I want to scale it. I want to rotate the image, right? I want to rotate the image. I want to make this image change into black and white, right? No? Black and white. So in all these things, we can actually perform some operation. We can do all these things with the help of linear algebra, because here also we will be transforming these images, right? We'll be transforming this specific images. So linear algebra is used to perform transformations such as scaling, rotation, and translation of objects in computer graphics. Okay. And again, it depends on what kind of dimensions you are specifically working in this specific image. Okay. Similarly, in 3D graphics also, if you want to convert a 3D model into 2D image, you can actually do it with the help of linear algebra. There also some of the other things will be coming up. Okay. One more very important concept that we really need to talk with respect to application is something called as optimization. Okay. Now in optimization here, we are basically solving equations. Now what kind of equations we'll be solving here? Okay. So any linear equation, let's consider an example of linear equation. One of the linear equation that I actually mentioned is equation of a straight line, y is equal to mx plus c. Okay. Now, if you just read about one of the algorithm which is called as regression. So for this y is equal to mx plus c, we will try to find the right kind of m value and right kind of c value. M is basically called as slope and c is nothing but coefficient. Sorry, c is basically called as intercept. M is nothing but slope or coefficient. I can also mention this as coefficient. Now, just to give you an example, let's say if I have a data set, here I have the size of the house, here I have price of the house. Let's say I have a lot of different data points. Our main aim is to draw a best fit line such that this line will be able to make sure that this line is like, it will take any input, it should take any size and it should be able to predict the house price. Okay. Now just think over this. Okay. If you really want to create this line, this is the equation of the line. Now for this line, you need to have the right m value and you need to have the right c value. Otherwise, you can create line in this way also. You can create the line in this way also. You can create the line in this way also. You can create the line in this way also. Why did I just select this line only? The reason is very simple, because the differences between these points, right? The differences between these points is minimal. If I do the summation of these differences or errors with respect to my training data, it is minimal. So how do I come up with this exactly best fit line? It is just by solving this linear equation wherein we try to find the right slope and intercept. Now this value will just not be solved by randomly selecting some values and populating it over here. No, we need to solve this entire equation, right? We need to solve in such a way that we will consider this as a function and we'll try to see, hey, when we are solving this particular function, when does this error come down? That will be my best fit line, right? So we will try to maximize this function and minimize the error. So this process is basically called as optimization. Okay. How this is done? I will be as we go ahead, we will be solving one linear regression theoretical intuition and how this entire things happen step by step. Here the concept of something called as gradient descent will be applied. Gradient descent. Okay. Very important topic altogether. Gradient descent. Okay. And this is basically called as an optimizer. So that is the reason we are talking about optimization. Okay. So we'll discuss about this as we go ahead. Not only this, even in deep learning, we have different optimization techniques and all. Okay. Now, I think we have discussed so many things over here, and still there are many applications that we can think of. But I know I have discussed many things, but this is just to give you an idea that why linear algebra is very much important. Like, it is the basic building block of all the techniques that we specifically learn in machine learning, deep learning, and neural networks, right? So going forward, I will start discussing about various important topics like scalar, vectors, matrices, mathematical operations. And remember, all these topics will be learned understanding the concepts in data science and taking multiple examples in data science, right? So yes, this was it from my side. I will see you all in the next video. Thank you.